This question says, a chemist fills a reaction vessel with 9.6 atmospheres of methane, 0.699 atmospheres of oxygen, 8.28 atmospheres of carbon dioxide, and 1.74 atmospheres of hydrogen at a temperature of 25 degrees C. Under these conditions, calculate the reaction free energy delta G for the following chemical reaction. And it asks us to use the thermodynamic information in the ALEKS data tab and round our answer to the nearest kilojoule. So essentially we have methane plus oxygen yields carbon dioxide and hydrogen. So this is the reaction that we're going after, and we need to find delta G, the free energy of it. Well, there's a couple things we need to do in order to solve this. The first thing is we need to realize that delta G is equal to delta G naught under standard conditions plus RT ln Q. And in this case, we can look at Q as the current conditions. So this is going to be products over reactants, and it's going to be under current conditions as opposed to under standard conditions. So this is how we relate the standard change in free energy with the non-standard under these current conditions of this pressures of these different gases. But before we can do any of this, we need to find out what the standard change in free energy is. And to do that, we do it just like the previous problem on this playlist. It's just the products minus reactants. So delta G naught equals the summation of N times the delta G naught of formation, that's an F, for the products, minus the summation of N delta G formation of the reactants. And as I said, there's a previous problem on the playlist where we do exactly this, and you've also done this for entropy and enthalpy. So delta G naught equals, well, let's look at our first product. It's CO2, and there's only one of them. So on the table, it's minus 394.4 kilojoules multiplied by 1. Plus, well, the next product is hydrogen. That's an element, so it has a free energy of formation of 0. So we're not going to include it. Minus the first product is methane, and if you look up on the table, there's one of them, so it's 1 times minus 50.5 kilojoules. And again, the second reactant is an element, so its free energy of formation is 0. So delta G naught under standard conditions here is equal to minus 343.9 kilojoules. Now we can use this in order to find it under the non-standard conditions given in the problem with Q. Well, let's take a look at how we're going to do that. The first thing is R. So R in joules is 8.31 joules per K. But there's a problem. Delta G naught is in kilojoules. So instead of using 8.31, we want to divide this by 1,000 and use 0.00831 kilojoules per K for R. So this is going to be our R. This is the standard one. This is in kilojoules. T, we're just going to add 273.15 to our 25 because it has to be in Kelvin. So it's going to be 298.15 K. So now we have R and we have T. What about Q? Well, Q is equal to products over reactants. In this case, they're all gases and we're given pressures. So it's the pressure of CO2 times the pressure of, well, I guess we don't need the time sign, pressure of hydrogen squared, because there's 2 of them, divided by the pressure of CH4 times the pressure of O2. So products over reactants, except it's non-standard conditions, so we're going to use these atmospheres. I'm going to leave the units out because Q is typically given as unitless. So here, the first one is CO2. We find its pressure up here, which is 8.28, times hydrogen. We find it up here, which is 1.74. Since there are 2 hydrogens, we need to square that. divided by CH4, which is 9.6, times O2, which is 0.699. When you plug those all in, you find that Q equals 3.7358. And I'm not going to worry about sig figs because this is round your answer to the nearest kilojoule. So this is basically the value of Q when we solve this problem. Well, now we have all of our variables. We have delta G naught. We found that from products minus reactants. We have R, that's a constant. We just converted it to kilojoules per K instead of joules per K. We have T, we found the absolute temperature in Kelvin. And we have Q, which is just products over reactants. So now delta G equals delta G naught, which is minus 343.9 kilojoules, plus R in kilojoules, 0.00831 kilojoules per K, times the temperature, 298.15 K, times the ln of Q, which is the ln of 3.7358. I'm just going to go ahead and do that so there's a clear distinction between the numbers, and that's a 7, even though it's kind of hard to see. Now, we just solve this. We use a calculator to take the ln, and we get delta G equals minus 343.9 kilojoules plus 3.2654 kilojoules. So when we take the ln of this number, multiply it by the 298.15 times the 0.00831, we get this number. And we find delta G for these non-standard conditions is equal to the nearest kilojoule, minus 341 kilojoules. So this is how we can find delta G on non-standard conditions.